All right then. So yes, let's get started with restoring division. All right, I'll explain what happens with the steps and all of that stuff. As we go along. So yeah, let's get started. So the big question that we have to answer today is 9 divided by 4 is equal to what? That is the big question here. We have to find what the remainder is. We have to find what the quotient is, and it's amazing. It's crazy. Okay, let's actually get started now. So in the Booth's multiplication, we would generally write 9 as m and then 4 as the q. Here it is flipped. The q here is 9, and 9 in binary is simply, I think, 1001, and then the d, that's what we call the 4 here, right? It's the divisor. Divisor is a 4, which becomes a 0100, right? And a minus d here, as we have always done, is in fact going to be the 2's complement, right? So 2's complement. So first we take the 1's complement, 1011, and add a 1 to that, which makes it a 1 plus 1 0, and then 1 plus 1 0 1 1. So that is what the 2's complement is of d. Now one thing that I want to point out here is that we don't necessarily care about the sign bit here. Or we don't necessarily sort of look at things and say that this is negative, this is positive. Division is unsigned. Okay, if you actually have negative numbers in division, generally what you would do is you would perform the division in an unsigned manner, and then you would add the negative value, then you would perform the multiplication with -1 to get a negative value. That's how that works. But yeah, division on its own is an unsigned process, right? We just have to get this minus d for our own sort of our own sake, to make life easy for us. That is the reason why we are doing the minus d thing here through 2's complement. But again, remember, we aren't necessarily looking at it as a sign bit. We are just looking at it as a negative. Okay, let's move on. And do not, for the sake of God, life, whatever, do not ever add any extra bits here, because they can, in restoring division specifically, they can cause a lot of problems. Okay, this same problem in non-restoring division would be a bit different. We will get to that, right? I'll of course do a side by side, not a side by side, an up to down or whatever kind of a comparison there, but let's move on. Okay, so look at the size of d. So d is 4 bits in length, so we write 4 zeros in the accumulator. The q is 9, which is 1001, and that's about it. You look at the size of q, which is 1 2 3 4. It has 4 bits, therefore you have to do 4 iterations. Amazing. Let's get started. It's very nice. Okay, now notice here, so in Booth's division, Booth's division Booth's multiplication, in Booth's multiplication, what we do is that we perform a right shift, but and that too, we perform the right shift at the end of the iteration. But here in division, to start the iteration, we actually perform a left shift. Okay, so let's get started. I mean, why wait? So 0001 001, and the next bit is a blank here in Q. Now you might ask why. The reason is we don't know what actually goes in here, right? Now you might also ask, what do you actually do here? That leads to like actual some steps and all that. So you look at the accumulator. So the accumulator right now is 0001, right? And it's okay, right? So now what you try to do is you try to subtract d from the accumulator, and you try to get a 0. Let's try to do that. So when you do that, you do 1100, and you try to actually perform the addition here, 1101. You'll notice that this is not 0 at all, right? We don't care what value this actually is, right? That does not even matter, right? That does not matter at all. The point is that this is not 0. But notice what happens in the hardware. Well, the hardware is hardware, right? And I mean, even I had to do it, of course. So the intermediate state was 1101 and 001 followed by a blank, right? Now this is not 0. So the hardware kind of goes, oh, this is not 0, and we are performing restoring division. So I have to basically go back to this state. So it restores. That is why it is called restore. So it performed an operation of subtraction, or not negative, sorry, subtraction. And here it has to perform the operation of addition to basically go back to what it originally was. Okay, right? And since it performed this restoring step, this bit here in the end that we had put a blank on becomes a 0. So now we say that the state now at the end of the iteration is 0001 followed by 0010, and the number of iterations that we have left is 3. That's it. Very simple, very nice and elegant process. There is nothing to do here. Again, we'll start the iteration again, perform a left shift at first. You have a 0010 and 010 along with the blank. Again, the same thing. So you look at the accumulator 0010 and you try to add a negative value to try to make it a 0. When you try to add minus d, which is 110 1100, right, again notice how it becomes 1110 1110. 1110 is not 000, but again what happens in hardware is that it gets converted to 1110 and 010 with a blank, and it panics. It goes, oh my god, I did a subtraction, I'm not a zero, I reverse this, right? So it performs two operations here, right? And since it performed restoring, it has to put a 0 here, and so the state now is 1110 followed by sorry, not 1110, whoops, that's my mistake. So the final state is 0010 followed by 0100, and we say that now we have two iterations to go. Awesome, let's keep going. Perform a left shift again. So 0100 100 with a blank, right? And now again 0100, you try to again add a negative. Okay, you try to add a negative, which is 1100 1100. Notice what happens here. So 00, 1 plus 1 is a 0, and then carry 1, of course. So 1 plus 1 now becomes a 0, and of course carry 1, so that goes here. Notice how these 4 bits become a 0. Now we don't care about this extra 5th bit that was produced, dump it in the garbage, but you look at these 4 bits, they became a 0, which is amazing, awesome. So the intermediate state now is 0000, and since we actually got zeros here, we celebrate by putting a 1 in this blank here, and that is where we end this iteration. So let me write it properly. So we say that now the current state is 4 zeros followed by 1001, and we have only one more iteration to go. Let's keep going, let's celebrate. So left shift again, so you have 000 followed by a 1, then you have a 001 followed by a blank, and again you take the accumulator which has 0001 in it. You look at what is it, minus d, which is 1100 1100. I mean, I don't have to do it, but you'll notice that the state will be negative and then 001 blank. It will get scared, it'll make a panic operation, not panic, it will basically perform a restoring step, right? And what we will end up with is 0001 followed by 0010, and then it will say that it has 0 iterations to go. Now notice, this is the final answer, right? Now in multiplications we would put these two registers together, but here in division, this accumulator is in fact our remainder, and this little q register is in fact our quotient. I'm not going to write the full word, but it's the quotient. Now let's perform our own verification. So the divisor was a 4, so let me write that. So 4 multiplied with, what is this value here? Let's look at the quotient. So it is 0010, which is 2. If I add, what is this remainder? Remainder is a 1. What is it? So 4 plus 2 is an 8. 8 plus 1 is a 9. Now if you look at the problem that we had, we can clearly verify that yes, this is in fact correct. The value that we were dividing with was was 9, and we have got back our 9, and therefore we have succeeded. This was restoring division. Actually a pretty simple algorithm. There is not a lot of stuff going on here, right? And that's about it. Now let's do non-restoring example in the next video, of course. Whoops.